Can you imagine that beneath the hustle and bustle of magnificent Paris, 20 TBM monsters, each over 100 meters long, are operating 24 hours a day, 7 days a week to create one of the largest and most ambitious infrastructure schemes on Earth? If you're a fan of mega projects and the cutting-edge tech that drives them, make sure to hit that subscribe button. We're diving deep into the mechanics of the world's most sophisticated construction site today. The Grand Paris Express, valued at $45 billion, with 200 kilometers of track on 4 new fully automated subway lines with 68 stations and 7 technical centers, is expected to serve approximately 2 million passengers per day. Technical analysis of the Grand Paris Express shows that this is not just a metro project, but a massive laboratory for urban tunneling engineering, where contractors operate dozens of TBMs simultaneously, at times with 20 machines working in parallel under the heart of Paris. This makes the GPE the project with the highest TBM density ever recorded in Europe. First, let's explore the geological characteristics of Paris and why TBMs, specifically EPB and Mixshield models, became the core solution for this project. The City of Light is a metropolis with over 2,000 years of history, possessing dense classical architecture sitting atop a complex, multi-layered geological foundation. To build over 200 kilometers of tunnels, Paris could not use the drill and blast method. The optimal choice was excavation using high-capacity TBMs, applying a suite of pressure control technologies, drilling in complex hydrological conditions, and assembling concrete segments through an automated cycle. 90% of the new lines being built will run underground, so there are 2 main types of TBMs used for construction. EPB Shield TBM, earth pressure balance, which is suitable for soft soil with high moisture, and maintains face stability using the excavated soil itself. And Slurry/Mixshield TBM, which is applied in areas with high-pressure groundwater or loose soil layers containing gravel and boulders. Before we break down the EPB components, I want to hear from you in the comments. If you were the lead engineer on a project of this scale, what would be your biggest concern? The groundwater or the sheer density of the city above? Next, let's look into the structure and function of the EPB components. The EPB and backup system are delivered to site in sections and lowered into the launch shaft where assembly takes place. Once assembled, a short starter tunnel is built to provide initial thrust and support for the machine. This is the process of assembling a massive EPB nearly 110 meters long, weighing approximately 1,700 tons, with a shield diameter of about 9.87 meters and up to 136 cutting edges. An EPB cutting wheel consists of a cutter head with a diameter of approximately 10 meters, fitted with disc cutters and scraper blades for specific geological types. EPB shields with its rotating cutting wheel. The tunneling machine breaks and removes the material from the tunnel face. In soft ground, the cutting tools not only cut, but also mix the soil with water, foam, and bentonite to maintain stable excavation conditions. The soil conditioning medium is injected through nozzles integrated into the cutter head. The entire system functions like a horizontal grinder, driven by enormous torque from electric motors, reaching around 10 meganewton meters. This level of torque is sufficient to twist and deform the equivalent of 15 steel shipping containers at the same time. Thrust is generated by hydraulic pistons, while the cutter head rotation speed is typically only about 2 revolutions per minute. Although this seems slow, each rotation removes several tons of soil and rock. Soil conditioning is considered the heart of the Grand Paris Express tunneling process. Excavating beneath Paris means confronting weak, water-bearing soils. To maintain stable face pressure, the soil must be transformed into a material with controllable plastic flow behavior. The project uses specialized foam such as Master Rock SLF50, combined with bentonite to create a waterproof membrane and polymers to increase cohesion when the soil is overly loose. As a result, excavation becomes less about drilling and more about controlling material flow. Freshly excavated soil is temporarily stored in the excavation chamber, located immediately behind the cutter head. Natural earth and groundwater pressure push the material into this chamber, forming the basis of the earth pressure balance concept, where excavation and ground support occur simultaneously. This approach is fundamentally different from traditional tunneling methods. Maintaining stable pressure within the excavation chamber is the most demanding requirement when tunneling in dense urban environments. The soil is transported with a screw conveyor driven by a negative 400 kilowatt power hydraulic motor from the invert of the excavation chamber to a belt conveyor. This component is not merely a transport device, but a critical pressure regulating valve. Even a millimeter level change in screw conveyor speed can significantly affect the pressure at the tunnel face. The entire system is continuously monitored using sensors that measure face support pressure, cutter head torque, screw conveyor torque, and the properties of the excavated material. Immediately behind the cutter head is the erector robot. The erector is mounted on 2 rails and can move longitudinally, rotate, and extend to install precast concrete segments into a complete ring. Each ring typically consists of 6 to 8 segments, plus a key segment that locks the ring. The Grand Paris Express segments are made of high-strength concrete rated at Class C 50/60. The total volume of concrete used for tunnel linings reaches approximately 650,000 metric tons. After each ring is installed, the annular gap between the lining and the surrounding ground is filled with high-pressure grout to prevent voids and surface settlement. The tunnel boring machine then pushes against the newly installed ring and continues forward. Behind the tunnel boring machine is the backup system, consisting of a series of modules extending over tens of meters. These modules house hydraulic power units, pumps, electrical switch cabinets, ventilation systems, laser guidance equipment, and storage containers for soil conditioning materials. A tunnel boring machine is only truly effective when supported by an equally sophisticated logistics system. Excavating 200 kilometers of tunnels corresponds to handling millions of cubic meters of material. As a result, each tunnel boring machine on the Grand Paris Express functions more like a mobile underground factory than a simple drilling machine. When tunneling is completed, the tunnel boring machines are dismantled and removed, but the project is only halfway finished. The next phase involves constructing stations and operational systems. Inside the tunnels, metro tracks, fire protection systems, emergency exits, and ventilation systems are installed. The Grand Paris Express is designed for fully automated, driverless metro operation, so the signaling system is digital by design from the outset. Communication-based train control technology allows headways to be reduced to around 120 seconds, with optimization targets approaching approximately 90 seconds, enabling up to 30 trains per hour. With the largest number of tunnel boring machines ever operated simultaneously within a historic urban environment, the Grand Paris Express is not just a transportation infrastructure project. It represents a new technical benchmark for European tunnel boring machine technology, where earth pressure balance systems, Mixshield machines, soil conditioning, and pressure control have been standardized at the highest level.